put it in the output range, and stick your, if you want to change, the default was the 95% confidence, almost always the default. You can change that if you want, or not. Let's see, we don't care about pH stat. So here's the example. Yeah, here's what got spit out. Yeah, so you got your intercept and your slope. Yeah, okay, and the rest of this stuff uses the same setup as the ANOVA does. So you recognize all this other stuff, you know, the F statistic. It's using the same setup. But here's your two coefficients down here that you're trying to dig out. And here's your R squared up here. So this wasn't the best fit. Yeah, 0.58 is not a real strong one. Let's see. But that makes sense. The data are kind of scattered. So yeah, there's your slope, your intercept. Let's see. So now what are they going to do with it? Oh yeah, they're explaining to you what's wrong with B0, right? Yeah, you can't have a 0 square foot house. And that's again, but that isn't a decent illustration of why I don't go outside your data range, right? That doesn't really make any sense. And I don't think that you have the choice. Let me see. Let me go back. I don't think you had the choice in the regression, did you? To let's see. Yeah. Yeah, right there. Yeah. So you could make it 0. So if you want to force it to go through 0, that may be something you want to do. You know, not the house prices, obviously, that probably didn't make any sense, but the thing I'm working on, I've got calculating the vibration force versus current in a motor, and I want to force it through 0. So obviously, don't turn it on, it's not going to vibrate. And so I've been using that, but I've been using MATLAB, so I wasn't sure if this did it. So let's see. Yeah, so here they're trying to estimate, right? No, they're telling you what the slope means, yeah. Here's it. So here. There. Here they're going to predict the price, yeah. So now you got 2,000 square feet, plug it in, there's your cost. Okay. That's not, yeah, we all know how to use a model. So here, and they're saying, yes, be careful again, don't use it out of the range. And again, I say you might be able to use it a little bit out of the range. If you do, put some thought into it, see what's going on and why are you doing that? Why do you not go ahead and take more data? You'll understand what it is your risks are going outside the range. Because in this case, you know, we probably know, you know, as you get in houses, it's probably true. As you get down here, the price probably starts really going up quickly. And down here, we know it stops. There's somewhere it kind of starts tapering off, and there's a minimum price, regardless of whether you make one of those micro houses that are kind of popular and cool now. All right, so I told you that they would break up the error. The reason they're doing this is so you can understand really what the R squared is, that measures the correlation fit. It's just a good thing to understand, because I've presented this kind of stuff in the past, and when I first did it, I didn't know what it meant. I just knew, I can play it like I can get a line, and the outcomes R squared. The closer it was to 1, the better it was. Invariably, somebody always asks you, what does it mean? And you know, I always felt weak saying, well, the closer to 1, the better it is. It's not, you know, so if you know what it means a little bit, you can go one step further and at least calm people down. Or because you know, if you say closer to 1, the better it is, and they're going to say, well, how close to 1? You know, is 0.8 20% worse than 1? No, it's not really. It's because it's not linear. But so anyway, so the total sum of the errors is every data point minus the average. So how far away you are from the average. Remember that was a set of view graphs we had in the, two chapters ago. And then there's the regression error. That's each of the predicted point, not the data point, but what the line would have predicted, the difference between it and the average value of all the data points, right? And then there's the square error. That's the difference between the data point and the predicted. Now, so you've got your total error. Yeah, how far each data point was away from the average, and it's split up into how far predicted is away from the average and how far the data point is away from the predicted. So let's see, they got words describing that, then they'll show a picture. So right, so the SST is the total, This is the explained, and then this is the unexplained. Okay, why do they use those terms? They're trying to set you up for design experiments in the future. But yeah, the total variation is self-explanatory, right? Each data point away from the mean. The explained is, well, that's the part we understand, the linear part. It's explained because that's what we thought. We had some linear relationship. The unexplained is these little random errors off of the line. Okay, so here's the picture that I think makes it really good and clear. So you have some data that had some average, and then it had some trend. So your total error is just the sum of each of your data points away from the average. But part of that is explained, if you will, because there's this linear relationship. You understand that, and that's what we're looking for. And then part of it is the unexplained, the difference, the random error. Yeah, so that's error, that's the regression, and then that's the total. So now I promised you we would use this to do something other than just have a pretty graph. So what's R squared? So this R squared that it spits out is the SSR ratio to the SST. What was that? This to that. So now you can see if the ratio of SSR to SST is 1, then it's all due to the line. Therefore, you didn't have any error. It was a great fit because, yeah, goodness gracious, there was no difference between the data points and the line anywhere. And any deviation now shows up here. This is going to be less than the ratio between this and this is going to be less than 1. So the further away from 1 it is, the worse the line is. So it's the R squared is this ratio to that, and explains a ratio of how much of the data variation is attributed to the trend you're trying to explore versus just random error. Okay, so that's, and you'll get more of that in design of experiments. So let's see, they got a few more view graphs. I can't remember what else. So yeah, there's some that are 1. And remember, it doesn't care whether it's a positive slope or negative slope, since it's doing the square of sum and all that. Both of these are 1, whether positive or negative. That's agreement. And then these are not 1. Yeah. Yeah. So, but they don't give you a number on either. And again, what I would do too, if I had a data set and I got an R squared at 0.95 and I was really concerned how good is it, I would play with it a little bit. Play with your data set, manipulate some of the numbers to see how bad it makes R be in your particular data set, and then you can get an idea. Here, there's no linear relationship. Yeah, Y doesn't depend on X, so yeah. So let's see. Yeah, so we're back to the house prices, right? So here was your R squared, 0.58, and they've taken the numbers out, actually, got them for you. So 58% of the variation in house prices is explained by the square foot function. And so what does that mean? Well, there's probably other things, right? And that's what this is telling you. There's other things like how many gold bathroom fixtures you put, or, did you use hardwoods or carpet? There's a lot of things and those things are somewhat related to square feet. More square feet, more bathroom, more hardwood, but not exactly. And so that's why I only 58% of the variation. That's a nice conclusion. Now you get to decide, do I want to just use this? Am I a realtor and I'm just going to use it as a rough guide? But if I was selling my house, I sure as heck probably wouldn't use what came out of this. Well, unless I had one of the bottom end, or over predicting. And so that's how you use this sort of stuff. I think that's all I was going to do out of here. Let me see if I can remember. Because there was 1 or 2 other. Oh yeah, okay. I was going to go this far to here. I was going to make the comment, hey, when you're using these regression things and you're doing a linear regression or you linearize nonlinearities, you're assuming that you do have some sort of linear relationship. And if you don't, or you want to explore this, you can plot your data, scatter plot, or you can do these box plots to find out if you're skewed. In fact, they go on and talk a little bit about a residual analysis, where you take the error between each of your data points and the predicted, and then you can examine these residuals for independence and normality using the box plots and using that normal probability plot. So if you want to get into that, you can, you can see are my residuals linear? So yeah, you would like them to be, are they independent? Yeah, you'd like them to be. So you can form these residuals, which is just the error between each of your points in the prediction, and check for the independence, check for that, check for normality with this normality plot, and do some further analysis if you worry about your regression, if you worry if it was accurate or appropriate or not. I tend to not do that. I tend to just look at it and say, well, is this a decent model, and do I want to use this or not, and go from there. So let's see. Yeah, all right. That's as far as I wanted to go with them. Now let me show you an example of a regression with Excel, and then we'll be finished. So let's see here. So what I did, rather than rather than coming up with some scenario about houses or anything, I made up a function, and let's see, I want to show you what function I made up. Oh, that's because, I'm not on the correct tab. That's why it's not making any sense. Okay. So, and I wanted to extend it beyond just linear regression because I felt like that's sort of limited, fitting a line. Our data are generally more complex than just y versus x. So what I did, I made my function y as a function of two variables, x1 and x2. Once you see 2, you could easily imagine I could have 20 in there, right? x3, x4, it's the same approach once you put in 2. So what I did, I gave an intercept, so we would have an intercept. I assigned a slope to x1, a slope to x2, and also a slope to the product of x1 and x2. Because I also wanted to show you how to handle a nonlinearity. So once you see I did the product of x1 and x2, this could have easily been x1 squared, x2 squared, x1 times x2 cubed, ad infinitum, right? I could have 50 columns of different variables, and I could still be using this regression analysis that you can fit these nonlinear things, believe it or not. Okay, so the first choice I did, and then we'll go through each of the sheets. Let's see. The first couple examples. Oh, and I added noise to it too. I forgot. Yeah, because that's important. We saw it, right, with the nice little plot showing the errors. If you have no noise, I'm going to get a perfect line. Well, I'd like to see this linear regression, this multiple regression thing in Excel. Show me. So my function has an intercept, a slope on each of these three things, and some noise. And noise is just random noise thrown on top of it. And then I did several different cases. So I've generated this fake data for a bunch of x1s and a bunch of x2s, and I made fake data. So what I've got 4 cases. The first case I did, and they're each of the sheets, we'll talk about it when we get to them. I did only a slope on x1 and x2 and an intercept, and I didn't have any part of my function having anything to do with the product of the two. But we want to explore this. And then the first case I did no noise. The second case I did noise. And then the next two I put a slope on x1 and x2, but I didn't act like I understood that, and I just fit x1 and x2. Then I did it correctly, and then I did another mistake that I'll show you. And so let's look at them, explore them. So let's look at each one, and I think we'll understand. And then I think this sheet's the one that's got the directions right. So here I've got a slope on x1 and x2. It's over here. So I've got an intercept of 1.5. The slope on x1 is 1. The slope on x2 is 2. No relationship on the product and no noise. Okay, so I generated some data down to row 32. If I can almost get them all, I can show them to you. And then here are the steps. You set up the data table, data analysis tab, regression. The Y input was just this column. The X input was those two. Select the whole thing, check the labels because I wanted the labels, and then told it to stick the output up there. And so you see what come out. And this is the kind of thing I would encourage you to do. If you're going to use this tool 2 years from now and you don't remember, well, spot my sheet or make yourself one up and do it. Because, if I have no noise and I have a slope of 1 on x1 and a slope of 2 on x2 and an intercept of 1.5, I sure want to see that coming out, don't you? If I can't get the perfect case to work, I don't know what I'm doing. If I don't know what I'm doing, I better not use it on my data because I'm really going to be bad. And so look, yeah, 1.5, slope of 1, slope of 2, where's my R squared? Oh gosh, it's beautiful, right? 1, perfect fit, no noise. Okay, I think I've got a hold of my tool. So now the next thing I'm going to do, let's throw a little noise on there. Why am I putting noise? Because that's my experimental data, right? I went and measured, that's my experimental error. So I'm going to do the exact same thing, but I'm going to put a little noise on it. So we should expect our R squared should change. And that's about the only thing, except my slopes and intercepts may have some error in them now, correct? Well, let's see. All right, so I got the same intercept, same slope, 10% noise. Well, I shouldn't say 10% noise. Yeah, 10% noise because it's relative to 1. So yeah, my R squared got a little less. Okay, yeah, because it had some noise. And my intercept's not quite 1.5, is it? My slope's not quite 1, and the slope on that was not quite 2, but they're close. But there wasn't very much noise. And if I was concerned how much noise is too much, well, play with it. That's why you can Excel, right? Make it 20%, 30%, see what happens. Or put more data points or less data points, see if it messes up. All right, good. So now let's explore this a little more. Maybe let's put some variation in there that we don't understand yet. Okay. All right, so now what did we do? So now I have data I've generated intercept of 1.5, slope of 1, slope of 2, and oh, I've got x1 times x2 is in my data. But I've only told it to analyze x1 and x2, not the product of x1 and x2. I'll show you how to do that in the next. So what happened? It's a total screw up, isn't it? I mean, look at it. Look at my intercept, look at my slope on each one. It's not correct. Okay. Now the question you might ask yourself is, well, what if I had this data? How would I know this is not correct? Well, that's what your brain and your scatter plot is for, right? If I scatter plotted this and I get that goofy intercept and now it's 2 slopes, and try to plot it on a 3D plot where it had x1 and x2 and y, it's not going to be a good surface. And I'm going to hate it because, well, look, I'm intercepting down here minus 64 and the real intercept is 1.5. It's not going to look pretty. Now the question is, how ugly is ugly? Well, it's pretty ugly because I had a factor of 1 on x1 and x2. If I had a factor of 0.01 on x1 and x2, it probably look pretty good. And because there's not much error getting added in by the product of x1 and x2, in this case I had quite a bit. So this is again where you're going to have to, if you're actually fitting data and you didn't know that x1 and x2 was in there, now you'd have to do some, you have to do some thinking or something else in the future. But at least here you say, okay, yeah, that's a mess up.
Where was the square input?
It was not. See, I didn't have it. I did. Oh, this. It's in the data that I created, but I didn't put it in my table because I'm acting like I don't know that it was there. So if you look at each of the data, I'll show you because I didn't really show you that good. If you look at how each data point is made, let's see, where did I get the other? Probably on the first sheet, it's probably the only one that's dotted in there. Oh yeah, because otherwise I keep making, since I got random numbers and I keep making new data, I think I say, yeah, so you can see what I've done. I've taken the intercept, the slope times x1, the slope times x2, that got this slope times the product of the 2, yeah, plus random noise. So the x1 and x2 appeared in the data I created, but not in the analysis on that sheet. And so let's see. So we were down here, but you'll see on the next sheet too. Let's see. So that was not where we were, was it? Yeah, that's a super duper screw up. Okay, so now let's say I understand it. Okay, so now you see the difference. Now I have recognized the error of my ways or whatever. I understand that for some reason x1 and x2, the product of x1 and x2 appears in that data. So here I've made a column of x1 and x2, simply the product of each of those. You'll notice things change down here. Just notice that my numbers change. And so now when I've selected my input to my regression, I've added 3 columns. Okay? You see it appeared another guy down here. And it has error, it has noise in it too. My R-squared is beautiful now. Oh yeah. And in fact, we should have known that on the last one. I think my R-squared probably stunk on the last one, didn't it? Let's see if it did. What was my R-squared? Yeah, 9.2. Yeah, it was a lot worse than what we've been getting. Yeah, so here's a beautiful R-squared, almost 1. My intercept is now not quite 1.5, but 1.6. X1 has got its slope of 1, X2 has got its slope of 2. The product has its slope of 1. So you can see how, again, now that you've seen how to include x1, x2, again, I can have x1 squared times x2 squared. Now, I better know that that's in my data or something, or do this analysis and find it out. It's a very useful tool, simple to use. Under your data analysis, when you saw this, it's very easy to use. Now, the last thing, though, I want you to be careful, mind what's wrong here. Okay, let's see what happened. Let's see, I've got 1.5 on my slope, on my intercept, 1, so the same old problem. In fact, I took the 0 out of x1 and x2. I have no noise. My R-squared is 1, my intercept is 1.5, x1 is 0, and x2 is 3. Let me shrink it up just a tiny bit, because I'm asking an unfair question.
This is your slope.
Well, let's see. So what's happening here? This is a pitfall you gotta be careful about.
This is your x1 slope is 0.
It did, didn't it? It's not though. It's not. I generated the data with this x1 and 1 and an x2 and 2. Do you notice what the x2 slope is?
Same thing as X1.
Your x2 slope is double of your x1.
Well, it's the sum of the slopes of x1 and x2. Yeah, the x2 here, 3. It's the sum of the slopes. Think about why it might have done that. Well, it's a subtle change in the way I did the data. You noticed in the other set, you may have noticed down about 15, x2, changed. I went backwards from 13, 14, 13, 12. I had, in this case, you see x1 and x2 are dependent. They're the same. Therefore, you can't distinguish a variation in one of them looks like a variation in the other. So it combined the two together is what it did. So what I'm telling you, be careful. If you have a set of data and one of your independent variables is dependent on one of the other independent variables, you messed up. You failed badly because, well, now you don't have it. It's not. You don't have another independent variable. Yeah, and so make sure when you collect your data that you don't have one of your pieces of data dependent on another in a strong way like that, or you'll get this. You combine the two together. You can't distinguish. It still is kind of right in a way, in a weird way. Yeah, it's all just due to x2. Had the same, got the intercept right and had a perfect R-squared. Yeah, I just, you didn't need this variable, or well, you didn't need one of them. You could, and you can see why. Well, it didn't matter. So that's something to watch out for. Make sure your independent variables are independent, or they won't show up. So, but it's an easy tool, I think. You can see, like I said, these things in here, you already understand them. They're the same things that got spit out in ANOVA. And really what you're digging out when you do the regression is just these numbers here and the R-squared. And the rest of them are ancillary numbers that Excel generates. But I think it's a simple tool you could use to get some very, like I said, very complex relationship. I mean, x1 and x2 could have been the sine, right? Sine squared. Sine squared, anything. Any function could have been thrown in there. And as long as you generated the right column of data, just simple tool, nice, useful thing to make yourself some models. And I've got one more thing I posted I want to look at. It's also got the same command for MATLAB if you want to use it. I actually didn't look it up in R this time. I'm lazy again. Too much plumbing. So that's good. That's it for today. And that's it for our year, right? So everybody, I said, have a good Christmas. I hope you like this stuff. I hope you use it. I don't think it's hard at this level.
You teaching economics?
That's what they told me.
Oh,
That's another one of these classes that you can use, I think.
what about design and experiments? Or are you making sick of us of it?
No, I'm hoping I teach that one, because that's a lot of this kind of stuff, but from the different perspective, you know, it's the other question. How do I set up my experiment so I don't have this problem, you know, so I can do things. So yeah, I'm hoping I'm doing that one. But yeah, you should love engineering econ, really. It's so clear, and it's so useful. I probably used it more than any subject ever, buying houses, buying cars, making decisions on things.
How does it differ from like a standard?
Oh, that's an excellent question. How is yours better than did anybody have engineering econ, by the way?
No.
So what you had it. Okay, I teach it like you've never had it, because I figure most people have already forgotten it. So you don't need to know a thing.
I haven't used it since I was in the class, so.
Well, but there is a clear demarcation between the advanced engineering econ class and what you had as undergrad. The undergrad quits at the evaluating a single project. Is this project a viable project or not? This class goes well beyond that. It does multiple projects because, you know, hey, I got project A, B, and C. I don't want to just know is A a good project, does it make money? I want to know which is better, A, B, or C. It does that. Because of that, then it adds on some more advanced economic topics like taxes and depreciation, which nobody talks about in an undergraduate class. Then it does some decision analysis with your engineering econ. So it goes well beyond a regular undergraduate class. But it's clear. The book I use, 15th edition, so, you know, the mistakes are mostly gone, and it's well done. So, yeah, you should look forward to it, because I feel like its view graphs and its subject is clear, real clear. The only thing that's not clear is depreciation. That's because it's not my fault. It's just stupid rules. You know, I didn't make the rules. I just teach them. But if you take depreciation from the perspective of, hey, it's just some dumb table that I looked up some number out of, okay, never mind that it's a weird rule. Yeah.
What was the title of
The book,
Sorry.
it's Advanced Engineering Economics by, you can shoot us an email. I tell you, I can find it in 10 seconds, because I think I've still got all the stuff on my, on this thumb drive here. Give me a second, I probably got the syllabus from last time.
Yeah.
Because I used this same thumb drive last year. There it is.
It might, for all the wife jokes I hear, I think I can tell if you're married to an engineer.
Thank you.
Well, my wife's well, you're the cousin. I don't want to argue with you.
So I work with a bunch of physicists, and one of them, like, this one scientist is like, the most, you know, like, in-depth, why does this particle behave this way? Oh, if only I had a chemist. I was like, you're killing me, I am a chemist. And so the next time a physicist
I have to email you. I don't know what that book is. Take it home and feed your dog.
But that's what I said is, oh, if only I had a physicist. Like,
Sorry.
they're the most arbitrary.
So all of life is out there. So people don't want to be married to engineers, huh?
No, but then when they do that. No, but I
Yeah, I
hear
thought about
like
making
the
Christmas
white
card.
jokes.
Just
Yeah,
people
like a
trolling, like your
dog
wife
sweater.
trolling you and
Not
sticking that
figuring
thing
out how to put some wire in the
side.
My wife is
I
actually
don't have
good.
Christmas trees.
Respectful. Funny.
Going
You
fire.
know, yeah.
But
I'm sure she won't go out. Because I was like, I could do anything.
Stand like this, like records, all of us.
She rolls your eyes when you're gonna buy a new lawnmower, but you have to do this statistical analysis on which one has the best life and which one costs less.
And
to
then she
operate.
really laughs when I buy it, and then the next year I'm fussing at it because I bought too cheap one, which is what I always do. The refrigerator was the worst, because I hated the refrigerator 2 days after I bought it. And you know, when I hate something, I'm always like, God, this is designed by an idiot.